Welcome back to this new video, and this time we're going to be taking a closer look to the graph of the log function and some of its properties, domain, range, etc. So, title of this video, Graphing Log Functions. So let us start by considering a standard function. Let's call it log base 2, just a choice, really. So consider y equals log base 2 of x. What's the graph of this? Graph. What does it look like? Well, I mean, the best way to do that is still, has always been, will always be, good old table of values. So x and y. I intend to take several values here to really illustrate the shape. So let's start with, say, -1. What is this? What is this? What is this value, -1? Let me replace x by -1 into here. So y would be log base 2 of -1, right? So I don't know what that is, so I'm going to change this into an exponential. How do I do this? Remember from the previous video, the base to the power of the other side equal the inside. So 2 to the y equals -1. Wow. I must raise 2 to a power to get -1. I think we have a problem with that. You see why? The graph of 2 to the something looks like this. If you remember from the previous video, right? This is the graph of 2 to a certain power. Now, the domain, of all this might actually be r, but the range is not. What is the range? It actually only lies above the x-axis. So how can the curve in red ever have a value of -1 for its y-axis? It can't. So D and E. It does not exist. 2 to the anything equals -1. You can try any value you want. 2 to the -1, that's 1 over 2, 1/2. 2 to the -10, that's 1 over 2 to the 10, 1 over 1024. It never is going to be negative. And of course, if you put in 0 or positive value, you are not going to get negative value, as the graph of this suggests. Okay, let's try 0. 0, I don't know what that is, so I'll say I'm looking for a value of y such that log base 2 is 0. Now what does that mean? I don't know, so I'm going to switch it to an exponential. 2 to the y equal to 0. Can you find a value of y such that if you raise 2 to that value, you're going to get 0? The answer is no, you can't. Look, again, the graph. Does this red curve ever touch the y value 0, which is right here, the x-axis? No, the x-axis is an asymptote. Once again, there is no such value. Ha! Let me try 1/2. Is there a y value when x is 1/2? Je ne sais pas. I don't know, so I'm going to go y equals log to the base 2 of 1/2. Is there a solution to this? Well, at least 1/2 is potentially on the y-axis for the red graph. So let us see. Let us change this to an exponentials as I like to do. 2 to the y is 1/2. 2 to the y is 1/2. But 1/2 is the same as 2 to what power? -1. Aha! 2 to the y is equal to 2 to the -1. The bases are now the same. What's the value of y? -1. Ah, finally, a value for this graph when x is 1/2. Let's try 1. what would be the y value when x is 1? Je ne sais pas, I don't know. No lo sé. So log base 2 of 1 is what I am looking for. So 2 to the y equals 1. But as we may know, 1 is actually 2 to what power? Haha, 0, 2 to the 0 is 1. Same base, 2 and 2. So now my y is 0. Let's try 2. Let's try 2. Y is equal to log base 2 of 2. Hey, don't I have an identity for that from the last video? Log base a of a, right? This is always equal to 1. Yes, if you remember that, good for you. Otherwise, we could do the transformation and we would actually get 2 to the y equals 2, which is 2 to the 1, of course. That means y is equal to 1. All right, let me get another value. I think it should be enough. We're starting to get a good feel of what this is going to look like. So 4, I don't know what that is. So y equals log of 4 base 2. So that's 2 to the y. We're starting to know how this works. 2 to the y equals 4. And 4 is 2 to the 2. Once again, same base. The exponents must be the same. So that means that y is 2. We now have a nice table of values and we can actually use it to sketch the graph of this function. So I'm going to do that. I'm going to try to do that in the very restricted space that I have on this very small whiteboard. So y-axis and x-axis here. All right. So, all right, my x are -1, 0. Here's 1. So 1/2 will be halfway over here. I'll have 2, 3, and 4. And my y values will be -1. I have 0. I have 1 and 2. 1 and 2. So we can make a graph that roughly looks like this. And we can put in the values. We said when x is -1, there is nothing. When x is 0, there is nothing. And here, where x is 1/2, I have -1. And then 1, 0. And then 2, 1. And then 4, 2. This graph is actually going to shape up in the following way. A bit like that, where this part is clearly leaning towards -infinity, going closer and closer to the y-axis. So you probably recognized here an asymptote for the graph. So a couple of pieces of information on this. X is equal to 0 is a vertical asymptote. Vertical asymptote. What else? Shall we take a quick look at the domain? What is the domain of this graph? Domain is all the set of x's that I can put in. As my table of values suggests, negatives and 0 are out. That's what I can see on the graph. The domain actually starts on the very right side of 0. So 0 excluded to infinity. As for the range, I don't really usually care so much for the range, but let's mention it in passing. This is all the y values, and this goes to -infinity, and this keeps on increasing forever. So this is all the values of y in this in the real number system. So remember that it's characteristic that these graphs have an asymptote. This one has it at 0. And now we're going to take a look at some variations of other log functions depending on if we tag along the constant, if we bring in a negative sign, and so on and so forth. All right. Okay. Good. So a little remark before we go on. The graph of log base 2, as we saw it, is extremely similar to the graph of ln of x, which is log base very close to 2 actually, 2.78. So log base e, right? So the graph of f of x equals ln x, which you may remember as log base e. You know this, but it's never wrong to actually emphasize, is extremely similar to the graph of log base 2. The reason why I mention it is because it's going to come back in several occasions in Cal 1. So, like this. Same shape as the log base 2. Right? So y equals ln of x. Good. Okay, so variations. Variations on the graph of ln. What happens when we throw in a constant and where we change the sign? The first one is y equals log base 2 of minus x. What will this look like? Well, again, we could do a table of values. What's going to happen here is that every x that we had, like minus a half, minus 1, sorry, 0, 1/2, and so on, is going to turn negative. So what we are going to get as a graph, is actually going to look like this. Yeah, change colors. Notice the same vertical asymptote at x is equal to 0. Also noticeable, could have noticed that before, it actually has a noticeable x-intercept. When is this actually equal to 0? When is y equal to 0? So x-intercept, that happens when y equal to 0. So that means that 0 equals log base 2 of minus x. Yep. Changing this to an exponential 2 to the 0 equal moins x. And 2 to the 0 being 1. 1 equals minus x. So x equals minus 1. So that's minus 1. Just like over here in the graph of ln, this could also have been verified to be equal to 1. Yes. All right, so scrolling down, what else do we have here? What if we put a minus in front of the log? Minus log base 2 of x. What happens here? So x, I should label my axes since I will ask you to do the same on your assignment on this. So minus log to the base 2 of x, change colors again, is going to look like this. So this time the asymptote does this. See how the curve is actually somehow inverted with respect to the standard log. And once again, we have the intercept here at positive 1. But it's the log of minus x. Good. I'm running out of space and I have a couple more to look at, so let me get rid of this. Those small boards have so little space for us to work on. So little. So C, I'd like to investigate the graph of y equals log base 2 of x plus 3. What happens if it's like the x plus h thingy that you guys saw in high school. So what would the graph of this look like? The x plus 3 is actually going to simply shift the asymptote. So you're going to get, I'm going to have to do this a little more to the left this time. So again, x and y. Now this will be the same graph as log base 2, but except that I got x plus 3 here. So what I want to do here, I want to say let x plus 3 equal to 0. Yep. So I'm going to find here that x is minus 3. And where the inside is 0 is where the asymptote lives. So now this is my asymptote at minus 3. Yes. All right, so here we go. I have enough space. Going to look like something like this. Same shape as the standard log base 2, same shape, but basically it's going to have this as an asymptote, so this leans closer and closer to the vertical asymptote, which is minus 3. So vertical asymptote at x equals to 3. We could also very easily, I guess, find both the x and the y intercept. How would you find the y intercept? Super easy. Replace x with 0. So 0 plus 3 is 3. Log of 3, that's where this is. Log base 2 of 3. As for the x-intercept, then I need to let y is equal to 0. So y-intercept let x-intercept let y equal to 0. I wrote it wrong. So 0 égale log base 2 of x plus 3. So 2 to the 0 is x plus 3. 2 to the 0 is 1. Bring that over. So minus 2 equals x. This would be our x-intercept in this case. All right. One more. One more. This time, y is equal to, let's take the 3 outside, log base 2 of x, but plus 3. Instead of having the plus 3 inside the log, let's have the plus 3 outside the log. What will that do? Well, log base 2, pretty standard. So what's going to happen here is simply that we're going to get the same shape, but it's going to be kind of pulled up, if you want. It's going to be like steeper. The ascent will actually be steeper, something more like I should change colors again, something more like this. Yeah, so closer to the y-axis. I should label my axes again, being careless here. And then its rise is actually slightly steeper, and that is because of the 3 right here. Once again, it might be interesting to try to find the x-intercept. So x-intercept. Once again, how do I find the x-intercept? Replace y with 0. Let y equal to 0. So that means that here y is equal to 0. So log base 2 of x plus 3 is equal to 0. Bring the 3 over. Minus 3 is this. change this to an exponential. 2 to the minus 3 equals to x, and 2 to the minus 3 is 1 over 2 to the 3, which is 1/8. So as you can see, the x-intercept now is way closer to the asymptote. Asymptote remains the same, but the curve got actually shifted closer to the asymptote and brings up its curve like much faster vertically. All right, so I have space for one last. Y equals minus the log of minus x. Let's put some minuses in the picture here. So what do I have here? X and y. X and y. So again, table of values on this. The minus x will basically shift, and the minus in front of it will shift again, so we have a double shift here. So it's going to look like this, where, once again, this is minus 1 like that. So different shapes depending on what happens. If you're not convinced that this is the shape, what do? Table of values. Except that my time is actually running pretty fast here, so I'm going to let you verify. If you want to put some x and some y's, you may use the calculator, and you will see that this is the shape. The vertical asymptote stays exactly where it was. Not this, this. All right, one last thing. I don't want this video to last too long. Okay, so one last thing. So I'm going to call this the change of base formula. So to conclude this video, I just want to introduce you to, well, there's going to be several rules about logs that we're going to study in our next video, but I just want to introduce you to the basic one that can actually help us sketch the graph of some of these functions, because as you know, our calculator is limited to calculating log base 10 and log base e. So basically here, I have a chance to get a formula that translates one into the other. It's actually quite convenient, and it goes like this. Log base a of, I should use another color, b. This is the same thing as ln of b over ln of a. Or maybe I should even put the a in a different color. Ln of b over ln of a. Now, this is also the same thing as log of b over log of a. The base of the log here is irrelevant. So, for example, too many colors. It's confusing. For example, suppose that you want to calculate an approximate value for, I have an example here with numbers. I have log base 4 of 3. So the calculator, like I said, can help you with log base 10 and log base e, which is the ln. It cannot help you with log base 4. But if I use this change of base formula, log base 4 of 3, that can actually be written as one of these two expressions. And the one that I have is base 10. So log base 10 of 3 divided by log base 10 of 4. You could have used the ln 3 over ln 4. It would have given you the same thing. And the values that I have are here. You can verify this on your calculator yourself. This is 0.476 7, 1, 2, etc. over 0.60205, and if that should also be a squiggly because it's not exact, it's approximate, I am leaving these ... at the end. And if you calculate the ratio of these, you are going to get approximately 0.79248 ... So that would give you an approximation, fairly good approximation, should you say, of log base 4 of 3. It's actually equal to this. So that's going to be useful when you sketch graphs and you want to sketch the graph, for example, of log base 4 of x, right? If you need a table of value, well, you need to know the y value, but since the calculator doesn't have log base 4, we can do this. Good. So we'll have more rules of logs in our next video, but for now, here we go. That's it for today. Be good, and I'll see you soon.